Dan Van Boxel, an engineer with 10 years of data mining and machine learning experience. I live stream my experiences with machine learning software weekly at Dan Does Data on YouTube and Twitter. My background is in civil engineering and mathematics, where I've published several modeling papers on topics ranging from traffic safety to hydrodynamic stress. I'm active in the open source community and have contributed to multiple projects, including TensorFlow. TensorFlow is a new machine learning and graph computation library recently released by Google. Its Python interface allows elegant design of common models, while the compiled backend ensures speed. This video provides a glimpse of the techniques we'll learn and models we'll build as we apply TensorFlow. This course is divided into sections of related videos. Each section will focus on a particular type of model in TensorFlow, often building on work of previous sections. Section 1 shows you how to install TensorFlow and build a simple classification model. Section 2 introduces neural networks and deep learning, developing them in the TensorFlow framework for the modeling problem. In Section 3, we learn about and apply convolutional neural networks, a popular technique appropriate for image-based classification. Section 4 demonstrates how to handle time series problems with recurrent neural networks. It also introduces a simplified interface to TensorFlow. Finally, Section 5 reveals the models you've built for the classification problem and describes how you can make the most of TensorFlow. Over the course of this series, you will learn how to use TensorFlow on a novel research problem. We'll study images of letters and digits in various fonts with the goal of identifying the font based on a single image of a single letter. This is a straightforward classification problem with data unique to this course. As no single pixel or position is important, but rather local structures among pixels, it's an ideal problem for deep learning with TensorFlow. Though we'll start with simple models, this series gradually introduces more nuanced approaches and explains code line by line. By the end, you'll have created your own advanced model for font recognition. While this course will show you how to install TensorFlow, there are a few dependencies. At a minimum, you'll need a recent version of Python 2 or 3 and NumPy. To get the most out of the course, you should also have matplotlib and IPython. And even if you're unable to install these, the next video shows you how to use TensorFlow entirely online. So put on your helmets, we're going deep into the data mines with TensorFlow. Welcome to Deep Learning with TensorFlow. In this section, we will learn what TensorFlow is, how to install it, and how to build simple models and do simple computations. Further, we will learn how to build a logistic regression model for classification and introduce a machine learning problem to help us learn TensorFlow. In this video, we're going to understand what is TensorFlow and how to start using it. We're going to learn what kind of library TensorFlow is and install TensorFlow on your own Linux machine or on a free instance of Sage Math Cloud if you don't have access to a Linux machine. First, what is TensorFlow? TensorFlow is a new machine learning library put out by Google that is designed to be very easy to use and very fast. If you go to the TensorFlow website, tensorflow.org, you can learn a wealth of information about what TensorFlow is and how to use it. We'll be referring to this often, particularly the documentation. Before we can get started using TensorFlow, though, we need to install it, as it probably doesn't come pre-installed in your operating system. So if you go to Get Started on the TensorFlow webpage and scroll down to pip installation, you can see how we're going to install TensorFlow. TensorFlow has been challenging to install even for experienced system administrators, so I highly recommend using something like the pip installation, or, if you're familiar, the Docker installation. You can install TensorFlow from source, but that can be very challenging. We will install TensorFlow using a provided precompiled binary called a wheel file. You can install this file using Python's pip module installer. For the pip installation, you have your option of using a Python 2 version or a Python 3 version. Also, you can choose between the CPU version and the GPU version. If your computer has a powerful graphics card, the GPU version may be for you. However, you need to check that your graphics card is compatible with TensorFlow. If it's not, it's fine. Everything in this series can be done with just the CPU version. So if you copy this line for TensorFlow, you can install it for Python 3.4. If you don't have Python 3.4 like the wheel file called for, that's okay. You can probably still use the same wheel file. First, you'll just need to download the wheel file directly, either putting that URL in your browser or by using a command line program such as wget. If you download that, it will very quickly be grabbed by your computer. Now, all you need to do is change the name of the file from cp34, which stands for Python 3.4, to whatever version of Python 3 that you're using. In this case, we're going to change it from a version using Python 3.5, so we'll change the 4 to a 5. Now you can install TensorFlow for Python 3.5 simply by changing the installation line here to pip3 install and the name of the new wheel file after changing it to 3.5. And we can see that works just fine. Now you've installed TensorFlow. If your installation somehow becomes corrupted later, you can always jump back to this segment to remind yourself how to install. If you don't have administrative or installation rights on your computer, but still want to try TensorFlow, you can try running TensorFlow over the web in a Sage Math Cloud instance. If you go to cloud.sagemath.com and create a new account, you can create a new project. This will give you a sort of virtual machine that you can play around with. Conveniently, TensorFlow is already installed in the Anaconda 3 kernel. Let's create a new project called TensorFlow, and we click Create Project. Now we can go into our project. It will take a couple seconds here to load. Go to Create a New File, and we'll create a Jupyter notebook. Jupyter is a convenient to interact with IPython session and the primary means of using Sage Math Cloud for these computations. Again, it may take a few seconds to load. When you get to this interface, the first thing you need to do is change the kernel to Anaconda Python 3. This will give you the proper dependencies to use TensorFlow. It may take a few seconds for the kernel to change. Once you are connected to the new kernel, you can import TensorFlow and do run cell to verify that it works. If your Jupyter notebook is taking a long time to load, you can instead create a terminal in Sage Math Cloud. Once there, type Anaconda 3 to switch environments, then IPython 3 to launch an interactive Python session. You can work easily here, although you won't be able to visualize output. Import TensorFlow, and off you go. In this video, we've learned what TensorFlow is and installed it, either locally or on a virtual machine on the web. In the next video, we will explore simple computations in TensorFlow. In the previous video, we installed TensorFlow. In this video, we'll learn how to perform simple computations. First, we're going to take a look at the tensor object type. Then we'll look at the graph understanding of TensorFlow to define computations. Finally, we'll run the graphs with sessions, showing how to substitute intermediate values. First, open up the simple.py code file included with this video. You're going to want to be copying and pasting lines from that file or retyping it yourself. This will be the standard method for most of this course. Now, let's import TensorFlow as TF. This is just a convenient way to refer to it in Python. You'll want to hold your constant numbers in tf.constant calls. For example, let's do a equals tf.constant1 and b equals tf.constant2. Of course, you can add and multiply these to get other values, c and d. TensorFlow numbers are stored in tensors, a fancy term for multidimensional arrays. If you pass TensorFlow a Python list, it does the right thing and converts it to an appropriately dimensioned tensor. Here, you can see that happening. v1 is a simple vector, a one-dimensional tensor, passed as a Python list of 1, 2. The dots here just force Python to store the number as decimal values rather than integers, and you could probably do without them. V2 is another Python list, 3, 4. M is a two-dimensional matrix made from a list of lists in Python, creating a two-dimensional tensor in TensorFlow. N is also a two-dimensional matrix. Note that this one actually has multiple rows in it. And finally, K is a true tensor, containing 3 dimensions. Note that the final dimension contains just one entry, a single 2x2 box. Don't worry if this terminology is a bit confusing. Whenever you see a strange new variable, you can jump back to this point to understand what it might be. You can also do simple things like add tensors together. Or you can multiply them element-wise, so each common position is multiplied together. For true matrix multiplication, however, you need to use tf.matemul, passing in your 2 tensors as arguments. Everything so far has just specified the TensorFlow graph. We haven't yet computed anything. To do that, we start a session in which the computations take place. Doing sesh.run nn evaluates the given expression and returns an array. Let's take a look at that just for a second. And you see we get our output here. When you're done using your session, it's good to close it just like you would a file handle. For interactive work, we can use tf.interactiveSession and then simply call m2.eval to get the value of node m2. And here we see that value. Not all our numbers are constant. To update weights in a neural network, say, we need to use tf.variable to create the appropriate object. Note that we also have to initialize all such variables with a special call, tf.initializeAllVariables, and then run that with sesh.run. This is to actually put a value into that variable. In this case, it will stuff a 0 value into the w variable. Let's just verify that w has that value. You can see that it's 0 on the left here. Let's see what happens when you add a to it. Recall that a is 1, so you get the expected value of 1 here. And let's add a again, just to make sure that we can increment and it's truly a variable. Now we see that w is holding 2 as we've incremented it twice with a. You can return or supply arbitrary nodes when doing a TensorFlow computation. Let's define a new node, but also return another node at the same time in a fetch call. First, we define e. Let's take a look at what e starts as. And you can see e is just 4. Now let's learn how you can pass in multiple nodes, e and d, to return multiple values from a sesh.run call. You can see our 2 values here on the left, e being 4 and d being 2. Now suppose we want to use a different intermediate value, say for debugging purposes. We can use feedDict to supply a custom value for a node anywhere in our computation when returning a value. Let's do that now with d equals 4 instead of 2. And you can see our result has changed, now it's 6. In this video, we learned how to do core computations with TensorFlow tensors. In the next video, we'll look at a logistic regression model. In the previous video, we studied basic computations with TensorFlow. Now you're going to build a real machine learning model. First, we'll see the proposed machine learning problem, font classification. Then we'll review a simple algorithm for classification called logistic regression. Finally, we'll implement logistic regression in TensorFlow. Before jumping in, let's load all the necessary modules. If you're copying and pasting to IPython, make sure your auto-indent is set to off, otherwise the indentations tend to get messed up for functions and things like that. The module tqdm is optional. It just shows nice progress bars. And we'll set a seed of 0 just to get consistent data splitting from run to run. With this course, we provided a dataset of images of characters from 5 fonts. For convenience, these are stored in a compressed NumPy file, datawithlabels.npz, that should be in the directory with this video. It will be copied into the other video directories as well. You can easily load these into Python with numpy.load. Train here holds the actual pixel values, scaled to 0 to 1, and labels holds the type of font that it was. So a 0, a 1, a 2, a 3, or a 4, as there are 5 fonts. You can print out these values to look at them, although that's not very instructive, as most of the picture is all zeros. Only the center contains the image. If you have matplotlib installed, now is a good place to import that, and we'll use plot.ion to automatically bring up figures when needed. Here are some example images of characters from each font. If your plot appears very wide, you can just easily resize the window. It's often more work to resize it ahead of time in Python than if you're simply plotting interactively. Okay, some of these fonts are flashier than others. In the dataset, each image is represented by a 36 by 36 2D matrix of pixel darkness values. 0 represents a white pixel, while 255 represents a black pixel. Everything in between is a shade of gray. Our goal is to decide which font an image belongs in, given that we have many other labeled images of the fonts. To expand the dataset and help avoid overfitting, we've also jittered each character around in the 36 by 36 area, giving us 9 times as many data points. It can be helpful to come back to this after doing later models. It's important to keep the original data in mind, no matter how advanced the final model is. If you're familiar with linear regression, you're halfway to understanding logistic regression. Basically, we're going to assign a weight to each pixel in the image. Then take the weighted sum of those pixels. Betas represent the weights here, and x represent the pixels. This gives us a score for that image being a particular font. Every font will have its own set of weights as they value pixels differently. To convert these scores into proper probabilities, that is the y's, we use what's called the softmax function to force their sum to be between 0 and 1, pictured here. Whatever probability is greatest for a particular image, we classify it into the associated class. You can read more about the theory of logistic regression in most statistical modeling textbooks. One good reference that focuses on applications is Bill Green's Econometric Analysis, 2012. Implementing logistic regression is pretty easy in TensorFlow and will serve as scaffolding for more complex machine learning algorithms. First, we need to convert our integer labels into one-hot format. This means instead of labeling an image with font class 2, we transform the label into 0, 0, 1, 0, 0. That is, we stick a 1 in position 2. Note the 0 up counting common to computer science, and 0 for every other class. And now we call our one-hot function. For the pixels, we don't really want a matrix in this case, so we'll flatten the 36 by 36 numbers into a one-dimensional vector of length 1296, but that comes a little bit later. And recall that we've rescaled the pixel values, which are between 0 and 255, to be between 0 and 1. Okay, now we should split our dataset into training and validation sets. This will help us catch overfitting later on. The training set will help us determine the weights in our logistic regression model, and the validation set will just be used to verify that those weights are reasonably correct on new data. Let's kick off the TensorFlow code by creating an interactive session right here. You're starting your first model in TensorFlow. We're going to use a placeholder variable for x, our input images. This is just to tell TensorFlow that we will supply the value for this node via a feed dict later on. Also note that we can specify the shape of this tensor and use none as one of the sizes. The none allows us to send an arbitrary number of data points into the algorithm at once for batch processing. Y-bar, likewise, will hold our known labels to be used for training later on. To perform logistic regression, we need a set of weights. In fact, we need 1,296 weights for each of the 5 font classes, giving us our shape. Note that we also want to include an extra weight for each class as a bias. This is the same as adding an extra input variable that always takes the value 1. With all these TensorFlow variables floating around, we need to make sure they get initialized. Let's call that now. Good job! You've got everything prepared. Now you can implement the softmax formula to compute probabilities. Because we set up our weights and inputs very carefully, TensorFlow makes this very easy with just a call to tf.matemul and conveniently tf.nn.softmax. That's it! You've implemented an entire machine learning classifier in TensorFlow. Nice work. Where do we get the values for these weights? Next time, we'll use TensorFlow to train the model. Hi, welcome to Logistic Regression Training. In the previous video, we built a logistic regression classifier, but didn't have weights for an accurate model. If you haven't looked at that model in a while, it may be helpful to review the previous video. In this video, we're going to use TensorFlow to optimize our model weights to fit our data. First, we'll learn about the loss function for this classifier and implement it in TensorFlow. Then, we'll quickly train the model by evaluating the right TensorFlow node. Finally, we'll verify that our model is reasonably accurate and the weights make sense. Optimizing our model really means minimizing how wrong we are. With our labels in one-hot style, it's easy to compare these with class probabilities predicted by the model. The categorical cross-entropy function is a formal way to measure that. While the exact statistics are beyond the scope of this course, you can think of it as punishing the model more for less accurate predictions. To compute it, we element-wise multiply our one-hot real labels with the natural log of the predicted probabilities, then sum these values and negate it. Conveniently, TensorFlow already includes this function as tf.nn.softmax cross-entropy with logits, and we can just call that. Note that we add a small error value, 1e-50 here, to avoid numerical instability problems. TensorFlow is convenient in that it provides built-in optimizers to take advantage of the loss function we just wrote. Gradient descent is a common choice and will slowly nudge our weights towards better results. This is the node that will update our weights. Before we start actually training, we should specify a few more nodes to assess how well the model does. Correct prediction is 1 if our model assigned the highest probability to the correct class and 0 otherwise. Accuracy averages these predictions over the available data, giving us an overall sense of how well the model did. When training in machine learning, we often want to use the same data point multiple times to squeeze all the information out. Each pass through the entire training data is called an epoch. Here, we're going to save both the training and validation accuracy every 10 epochs. Note that we use the feed dict to pass in different data to get different outputs. Finally, trainStep.run updates the model every iteration. This should only take a few minutes on a typical computer, much less if you're using a GPU and a bit more on an underpowered machine. And now you can see it training here, and it will be done in just a few more seconds. You just trained a model with TensorFlow. Awesome. After 1,000 epochs, let's take a look at the model. If you have matplotlib installed, you can view the accuracies in a graphical plot. But if not, you can still look at the final number. Here, let's do that. We're going to set the figure size so that it's not too wide, hopefully. It seems like the validation accuracy flattens out after about 400 to 500 iterations. Beyond that, our model may be overfitting or not learning much more. Also, even though the final accuracy of about 40% might seem poor, Recall that with 5 classes, a totally random guess would only have 20% accuracy. With this limited data set, the simple model is doing all it can. It's also helpful to look at the computed weights. These can give you a clue as to what the model thinks is important. Plotting them by pixel position for a given class, we get an image like this, and again, you can square it up pretty easily. We see that the weights near the interior are important in some models, while the weights on the outside are essentially flat. This makes sense since none of the font characters reach into the corners of the image. Your final results might look a little different due to random initialization effects. Always feel free to experiment and change parameters of the model. That's usually how you learn something new. In this section, we have installed TensorFlow onto a machine we can use. After some small steps with basic computations, we jumped into a machine learning problem, successfully building a decent model with just logistic regression and a few lines of TensorFlow code. In the next section, we'll see TensorFlow in its prime, deep neural networks. Welcome to Section 2, Deep Neural Networks. Last time, we looked at simple TensorFlow operations and using logistic regression on our font classification problem. In this section, we will dive into one of the most popular and successful machine learning approaches, neural networks. Using TensorFlow, we'll build both a simple and deep neural net to improve our model of the font classification problem. In our first video, we're going to review basics of neural networks. We're going to learn common ways to transform input data, understand how neural networks connect these transformations, and finally, how to implement a single neuron in TensorFlow. Our logistic regression model worked well enough, but was fundamentally linear in nature. Doubling the intensity of a pixel doubled its contribution to the score, but we might only really care if a pixel is above a certain threshold or put more weight on changes to small values. Linearity may not capture all the nuances of the problem. One way to handle this issue is to transform our input with a nonlinear function. Let's look at a simple example in TensorFlow. First, be sure to load the required modules and start an interactive session. Here, we create 3 5-long vectors of normal random numbers, truncated to keep them from being too extreme, with different centers. Note that because this is random, your values are probably going to be a little different, but that's perfectly fine. A common transformation is to square the input. Doing this makes larger values even more extreme, and of course makes everything positive. You can see the result here on the left. Conversely, if you need more nuance among your small values, you can try taking the natural, or any base, logarithm of your inputs. Check that out here. Note that large values tend to become squished together, while the smaller values are a little more spread out. But the logarithm can't handle negative inputs, and the closer you get to 0, the more extremely negative your small input becomes. Be careful with logarithms. Finally, there's the sigmoid transformation. Don't worry about the formula. Just know that extreme values, positive and negative, get squished to +1 or 0 respectively, and inputs closer to 0 become closer to 1/2. And here you see an example that's become close to 1/2. Started at 1/4 and is almost 1/2 now. In machine learning, we often call these transformations activation functions, and we usually combine weighted sums of inputs into them. When you consider the inputs, weights, and activation function, that's called a neuron because it's inspired by biological neurons. The details of how real neurons work in a physical brain is beyond the scope of this course. If you're interested in that, a neurobiology text might contain more. Or you can take a look at Gordon Shepard's Foundation of the Neuron Doctrine as one recent reference. Let's look at a simple example in TensorFlow. First, just create some constants, W1 and W2. We're going to multiply x1 by W1 and x2 by W2. Then we add these intermediate values and finally put the result through this sigmoid activation function with tf.sigmoid. Take a look at the result. Again, don't worry about the exact formula right now. You can have a variety of different activation functions. Just note that this is your first step towards your own neural network. So how do we go from a single neuron to a whole network? Easy. The input of one neuron just becomes the input for another neuron in the next layer of the network. Here, we've got a simple network with two inputs, x0 and x1, two outputs, y0 and y1, and three neurons in the middle. The value in x0 gets sent to each of the n neurons, but there's a different weight, the value multiplied with x0, associated with each. x1 is also sent to each neuron and has its own set of weights. For each neuron, we compute the weighted sum of inputs, put this through the activation function, and produce an intermediate output. Now, we do the same thing, but consider the neuron outputs to be the y's inputs. Note that by taking nonlinear activations of weighted sums of inputs, we effectively just compute a new set of features for our eventual model. Now we've learned the basics of nonlinear transformations in TensorFlow and what neural networks are. While they may not let you read minds, they are crucial for deep learning. In the next video, we're going to use a simple neural network to improve our classification algorithm. In the previous video, we learned about the basics of neural networks. Now it's time to put them into practice. We're going to adapt the logistic regression TensorFlow code into a single hidden layer of neurons. Then we'll learn the idea behind backpropagation to compute the weights, that is, train, the net. Finally, you'll train your first true neural network in TensorFlow. The TensorFlow code for this video should look familiar. It's just a slightly evolved version of the logistic regression code. Let's look through how to add a hidden layer of neurons that will compute nonlinear combinations of our input pixels. You should start with a fresh Python session. Execute the code to read in and set up the data as in the logistic model. It's the same code, just copied to the new file. It's totally normal to pause, go back to that section, and remind yourself what that code does. Everything up to the variable num_hidden will get you up to speed. First, let's specify how many neurons we want with num_hidden equals 128. This is essentially how many nonlinear combinations will get passed to logistic regression in the end. To accommodate this, we also need to update the shape of the W1 and B weight tensors. They're now feeding into our hidden neurons, so they need to match shape. The way we compute the activation function of the weighted sum is with this single h1 line. This says to multiply our input pixels by their respective weights for each neuron, add the neuron bias term, and finally put this through the sigmoid activation function. At this point, we have 128 intermediate values. Now, it's just your friend logistic regression again. You already know what to do. These newly computed 128 features need their own set of weights and biases to compute a score on the output class. That's W2 and B2 respectively. Note how the shape matches the shape of the neurons, 128, and the number of output classes, 5. In all these weights, you probably saw that we initialized them with this strange truncated normal call. With neural networks, we want to get a good spread of initial values so our weights can climb to meaningful values, rather than just getting zeroed out. Truncated normal pulls random values from a normal distribution with the given standard deviation, a research standard scaled to the number of inputs, but throws out values that are too extreme, hence the truncation part of this. With our weights and neurons all defined, we set up the final softmax model just as we did before, except we need to take care to use our 128 neurons as the input, H1, and the associated weights and biases, W2 and B2. The key to training the weights of a neural network and many other machine learning models is called backpropagation. A full derivation is beyond the scope of this series, but let's go through it intuitively. When you train a model like logistic regression, an error in your training set directly comes from poorly chosen weights. You can see which weights should be adjusted by how much and change them accordingly. Formally, TensorFlow does this by computing the derivative of the error with respect to the weight and adjusting the weight a fraction of this. Backpropagation is really an extension of the same process. You start at the bottom, output or cost function layer, computing derivatives, and use those to compute associated derivatives with neurons one layer up. We can compute the appropriate partial derivative of the cost with respect to the weight we want to adjust by adding up the product of the derivatives on the path from the cost up to the weight. The formula here just spells out what the red arrows show. If this seems complicated, don't worry. TensorFlow handles it for you behind the scenes with the optimizer. Because we carefully specified our model, using TensorFlow to train is almost exactly the same as before. So we're going to use the same code right here. One thing to note is that because we have these hidden neurons, there are many more weights to fit the model. This means that our model will take longer to run and that it has to take more iterations to train. Let's run it through 5,000 epochs this time. This model will probably take longer than the last one, maybe 4 times as long, so you can expect a few minutes to 10 minutes, depending on your computer. With the model training now, we'll save checking out the accuracy for later. In this video, we built and trained a neural network in TensorFlow. You're now on the cutting edge of machine learning. In the next video, we'll take a close look at the model we just trained. In the previous video, we built and trained our first neural network with TensorFlow. In this video, we're going to carefully look at the model we built. First, we're going to verify the overall accuracy of our model. Then, we're going to see where the model goes wrong. Finally, we'll visualize the weights associated with several neurons to see what they're looking for. Make sure you've trained your model as done in the previous video. If not, you might want to pause here and do that first. Because we evaluated our model accuracy every 10 training epochs and saved the result, it's now easy to explore how our model has evolved. Using matplotlib, we can plot both the training accuracy, blue dots, and testing accuracy, red X's, on the same figure. Again, if you don't have matplotlib, that's okay. You can just look at the array values themselves. Notice that the training accuracy is usually a little better than the testing accuracy. This isn't surprising since the test images are totally new to the model and may contain previously unseen features. Also, observe how the accuracy generally climbs over more epochs. Moving up, first quite a bit, and then slowly advancing. Our model here achieves about 60% accuracy. Not perfect, but an improvement over the simple logistic regression. To see where our model is getting mixed up, it's helpful to create the confusion matrix. That is, we're going to see for an actual font class of 1, say, what did the model classify it as? Formally, we create a 5 by 5 matrix. For each testing image, we increment the value in position ij if the image was actually class I and the model predicted class j. Note that when the model gets this correct, I equals j. A good model will have big values on the diagonal and not much elsewhere. This type of analysis makes it easy to see if two classes are often confused for each other, or if some classes are rarely chosen by the model. Here, we create the predicted classes by evaluating y, the class probabilities. numpy.argmax extracts the position with the largest probability. Similarly, to determine the actual class, we use numpy.argmax to undo the one-hot encoding. Creating the confusion matrix starts with an all-zero array, and we step through the testing data, filling it in. Matplotlib lets us look at a color image, but printing the conf array is nearly as effective. Here, we see that the model generally does a decent job, except that it rarely predicts class 2. Your exact results may look a little different because of initial randomness. Just like we viewed the weights for a logistic regression model, we can spy on the weights for this model. Now, however, we have 128 neurons, each with 36 by 36 weights coming from the input pixels. Let's look at a few of them to get a feel for what they're finding. Again, if you don't have matplotlib, you can simply print out the arrays to see the same behavior. Here, we're going to look at 32 of the 128 neurons. So let's format our subplot into 4 rows of 8 columns. Now we step through each neuron, evaluating its weights and reshaping them into the image size. The double slashes put the image into the appropriate row using integer division, while the percent sign uses the remainder, really modular arithmetic, to pick the column. Visually, you can see some shapes sticking out. Some neurons have more or less a circular shape to their weight patterns. Others look random, but might be picking up features that we can't easily intuit. We can try to visualize the weights of the output layer as well, but these are no longer intuitive. Recall that because of our neural network, the output logistic regression is now 128 input values, along with weights being used to compute 5 scores. There's no longer an image structure since every pixel went into every neuron on the hidden layer. Now you know how to assess and interpret neural network results. Good job! In the next video, we take neurons a step further with a multiple hidden layer model. In the previous video, we studied a neural network with one hidden layer of neurons. In this video, we show you how to build even more complex models with additional hidden layers. We're going to adapt our single hidden layer model into a multi-layer model known as a deep neural net. Then we'll discuss choosing how many neurons and how many layers to use. Finally, we'll train the model itself, being patient as this may take a while to compute. Remember when we added a hidden layer of neurons to our logistic regression model? Well, we can do that again, adding another layer to our single hidden layer model. Once you have more than one layer of neurons, we call this a deep neural network. But everything we learned before, we can apply now. As in video 2.2, you should make a fresh Python session and execute the code up to numHidden1 in this video's code file. Then the fun starts. Let's start by changing the old numHidden to be numHidden1 to indicate the number of neurons on the first hidden layer. Make sure to change the variables defining the weight and bias variables as well. Now we insert our second hidden layer. Let's use one with 32 neurons this time. Note how the shape of the weights must account for every one of the 128 intermediate outputs from the previous layer coming into the 32 inputs or neurons of the current layer. But we initialize our weights and biases essentially the same way. And we create the H2 output with a sigmoid function just like we did before, with a matrix multiply, addition, and function call. For the output logistic regression layer, we just need to update the variable names. These are now the third set of weights, and of course the shape must match the output of the preceding hidden layer, so 32 by 5. Don't forget to update the model function y with the h2, w3, and b3 variables. You wouldn't want to update all the code only to use an old model. You might be wondering how we decided on 128 neurons for the first layer and 32 neurons for the second layer. The truth is that determining a good size and shape of your network can be a challenging problem. Though it may be computationally expensive, trial and error is one way to develop a model. Typically, you might start with an old model and work from there. Here, we started with the single hidden layer of 128 neurons and tried adding a new layer underneath. We want to compute some features to discriminate 5 classes, so we should keep that in mind when picking a number of neurons. Generally, it's better to start small and work your way up to a minimal model that explains the data. If a model with 128 neurons on the top layer and 8 neurons on the next layer does poorly, that may indicate that we need more features for the final layer and should add more neurons, not fewer. Try doubling the number of neurons in the final layer. And of course, it's good to go back to earlier layers and tweak the number of neurons there too. Likewise, you can change the learning rate of the optimizer, which changes how much the weights get adjusted at every step, and even change the function used for optimizing. Setting all these values is called hyperparameter optimization, a hot topic in machine learning research. Note that we're essentially starting from the simplest possible model, logistic regression, and slowly adding on new features and structures. If a simple model works well, it may not even be necessary to spend time on something more advanced. Now that our model is specified, let's actually train it. Again, we need to redefine our training nodes in the TensorFlow graph, but these are exactly the same as before. Note that because our first hidden layer now hooks into another layer of neurons, we have many more weights to compute. Before, we had 128 times 5 weights, but now we have 128 times 32 weights, over 6 times as many for this layer, and this is on top of the initial weights from pixels to the first layer of neurons. One downside of deep neural nets is they can take a while to train. Here, we're going to run for 25,000 epochs to ensure the weights converge. This may take an hour or longer depending on your computer and GPU. While this might seem excessive, professional machine learning researchers often train models for up to 2 weeks. You might learn quickly, but the computer takes a while. We'll evaluate how well this model did in the next video. In this video, we built and trained a truly deep neural network using TensorFlow. Many professional machine learning models are less complicated than what you've written already. In the next video, we're going to explore the results of our multiple hidden layer model. Hi, welcome to Multiple Hidden Layer Results. In the previous video, we built and trained a deep neural network. Now, we're going to understand what's going on inside it. First, we'll check the model accuracy. Then, we'll visualize and study the pixel weights. Finally, we'll look at the output weights as well. After you've trained your deep neural net, let's take a look at the model accuracy. We'll do this the same way that we did for the single hidden layer model. The only difference this time is that we have many more saved samples of the training and testing accuracy, having gone for many, many more epochs. As always, don't worry if you don't have matplotlib. Printing parts of the arrays is fine. Here, we reach about 68% training accuracy and maybe 63% validation accuracy. This isn't too bad, but it does leave room for some improvement. Let's take a moment to look at how the accuracy grows over many epochs. Of course, it starts terrible and it has some initial troubles, but the weights are random and still learning at that point. And it quickly improves over the first several thousand epochs. While it may get stuck in local maxima for a time, it usually climbs out and eventually slows its ascent. And note that it still climbs well into the training period. It's only near the end here that the model may have reached its full capacity. Your curves might look a little different based on random initialization, but that's okay. It's your model, and it's pretty good. To see where our model is having trouble, let's look at the confusion matrix. Again, this is exactly the same process that we used for the single hidden layer model, just on something a little more advanced. Plotting this, we see that the model is doing well overall, but still has trouble identifying one of the classes, this time class 1. We're making incremental progress. With the accuracy verified, let's check out what kind of phenomena our first layer of neurons, those 128 guys, are finding. For simplicity, we're only going to look at the first 32 such neurons. Using the same code from the previous model, these are easy to plot with matplotlib or printout. Not surprisingly, we see many of the same kinds of features as in the last model. Although here, they're going to be in different positions even if it looks like the same type of feature. Again, due to the random initializations. And again, you've got some circular type neurons, you've got neurons that find these very stripy features, and another neuron here that finds sort of broad stripes. As far as our neural network is concerned, circular shapes and stripy shapes are good ingredients for determining font class. While the weights in our other hidden layers no longer have the structure of an image, it can be instructive to look at the weights of the output. This will tell us how much each final neuron contributes to each class. We can plot this as one heat map or print a single array, either way using w3.eval. Because we carefully specified w3, each row will represent one neuron, and each column will represent one class. We can see that different neurons contribute more to some classes than others, indicating that certain overall nonlinear features the neuron is computing relate to that particular font class. That is, while the values these neurons produce are used to compute the scores for every font, a neuron that's very important, has a large weight, for one font might be nearly irrelevant in another font. For example, this neuron has a very large weight for class 0, but has almost 0 weight for all the other classes. Whatever feature this neuron is computing is very important to class 0, and not so much for the other classes. In this section, we have embraced deep learning with TensorFlow. Though we started with a simple model of one hidden layer of neurons, it didn't take you long to develop and train a deep neural network for the font classification problem. In the next section, we're going to improve our model with convolutional neural networks, a powerful tool for image classification. Hi, welcome to Convolutional Neural Networks. In the last section, we explored deep neural networks, which required ever more parameters to fit. This section will guide you through one of the most powerful developments in deep learning and let us use some of our knowledge about the problem space to improve the model. First, we're going to explain what a convolutional layer is in a neural net, followed by a TensorFlow example. Then, we'll do the same for what's called a pooling layer. Finally, we'll adapt our font classification model into a convolutional neural net and see how it does. Now let's jump into just what a convolutional layer is. In this video, we're going to walk through using a convolutional layer on an example image. We'll graphically see how a convolution is just a sliding window. Further, we'll learn how to extract multiple features from a window as well as accept multiple layers of input to a window. In a classic dense layer of a neural network, for a given neuron, every input feature gets its own weight. This is great if the input features are totally independent and measure different things, but what if there's structure among your features? The easiest example to imagine this happening is if your input features are pixels from an image. Some pixels are next to each other, others are far away. For tasks like image classification and font classification especially, it often doesn't matter where a small-scale feature occurs in an image. We can look for small-scale features in a larger image by sliding a small window throughout the image, and this is key, using the same weight matrix no matter where in the image this window is positioned. In this way, we can always look for the same feature anywhere. Suppose we have a 10 by 10 image on the left here, and we want to slide a 3 by 3 window through it. Typically, machine learning engineers will slide this window by just one pixel at a time. This is called the stride. So there's some overlap from one window to the next. Then we element-wise multiply our small 3 by 3 weight matrix, W1, into our window, sum the result, and put it through an activation function called f. This first window goes into the first position of a new matrix, shown here in orange. The window slid over one uses the same weights, but the result occupies position 2. Note that we're essentially using the upper left pixel as the reference point for where we store the result. Slide your window around the whole input image to generate the convolutional output. The dots here are just a reminder that you'll be sliding this window around the whole space, not just the two positions shown here. You might be wondering what happens when our window reaches the edge of the image. The choice is essentially to go between ignoring windows that go over the edge and padding them out with placeholder values. For convolutional layers, the common choice is to pad them out, often with zeros or an average value. This is called same padding in TensorFlow, so called because the output shape of your convolution remains the same. Note that in your final window, this is really only looking at one value, but that pixel took part in many other positions, so don't feel like it's been left out. The previous slides featured a single set of weights for the sliding window. This essentially lets you compute a sliding feature, but you probably want to look for multiple things in the same window, like vertical or horizontal edges maybe. To extract multiple features, you just need to have additional weight matrices, all initialized differently. These multiple sets of weights are analogous to additional neurons in a densely connected layer. Each matrix of weights, blue and green in the center, will gain you another matrix of output for additional use, shown here in pink and orange on the right. Just as you can pull multiple features out of a convolution, you can put multiple features into such a network. The most obvious example is in an image with multiple colors. You really have a matrix with red values, a matrix with green values, and a matrix with blue values. Your weight matrix is really now a weight tensor of size 3 by 3 by 3 with a window of the same size across the colors. Of course, you can combine all these approaches, and this is typically done, especially after your first convolutional layer. When you've computed, say, 32 features on the window, now you have many input channels for the next layer. In this video, we tackled the practical aspects of understanding convolutions. They can be convoluted, but hopefully no longer confusing. In the next video, we're going to apply these concepts to a simple example in TensorFlow. In the previous video, we looked at the background of convolutional neural nets. Now, let's implement a simple convolutional layer in TensorFlow. First, we're going to go over the explicit shapes used in this example, since that's often tricky. Then, we'll walk through the implementation and TensorFlow call for convolutions. Finally, we'll visually inspect the results of our convolution by passing in a simple example image. Let's jump right into the code with a fresh IPython session. This is just a small example to help us get familiar with using TensorFlow for convolutional layers. After importing the necessary tools, let's make a fake 10 by 10 image, but with larger values on the diagonal. Note the unusual size specified here. The 10, is just the image dimensions, but the 1 refers to the number of input channels. In this case, we're using one input channel, which is like a grayscale image. If you had a color image, this might be 3 channels to represent red, green, and blue colors. Though the example here and the research problem only have one channel, grayscale, we'll see in a later video how producing multiple outputs from a convolutional layer leads to a multi-channel input on the next convolutional layer, so you'll still get a feel with how to handle that. Moving down to the TensorFlow placeholder, we also do something that might seem unusual. Right after writing the placeholder variable in a natural way with 10 by 10 and none for the possible batch processing of many images, we call tf.reshape. This is to rearrange the dimensions of our image and get them in a shape TensorFlow expects. The -1 just means to fill out the dimension as needed to maintain overall size. The 10, of course, is our image dimension, and the final 1 is now the number of channels. Again, if you had a color image with 3 channels, this would be a 3. For our convolutional layer example, we want to look at windows of the image that are 3 pixels tall and 3 pixels wide, so we specify those here. Also, Let's extract 2 features from each window. So that's our number of filters. You might also see this called the number of kernels. Specifying the weight is where things get really interesting, but it's not hard once you know the syntax. We're using tf.truncatedNormal as we did before to generate random weights, but the size is very peculiar. WinX and WinY are of course the dimensions of our window. 1 here is the number of input channels, so just grayscale, and the final dimension is the output dimension, the number of filters. Again, this is analogous to the number of neurons for a densely connected layer. For the standard deviation on the randomness, we still scale to the number of parameters, but note that we have a parameter for each weight, so WinX times WinY. And the bias, of course, needs a variable for each output neuron, so 1 for each filter. tf.nn.conv2d is really the heart of the operation here. We first pass in our reshaped input, xim, then the weights that are applied at every window, and then this strides argument. Strides tells TensorFlow how much to move your window by at every step. Typical usage for convolutional layers is to shift by 1 pixel to the right, and when you finish a row, shift by 1 pixel down. So there's a great deal of overlap. If you want to shift by 2 pixels to the right and 2 down, however, you could input strides equals 1, 2, 2, 1. The last number is for moving over channels, and the first is for moving over separate images in a batch. Setting these to 1 is the most common approach. The padding equals same is exactly as described in the last video. This means that the sliding window will run even if part of it is beyond the bounds of your input image. Combined with a stride of 1, this means that the convolutional output dimensions will be the same as the input, not counting the number of channels nor filters, of course. Finally, we want to pass this convolutional output through an activation function. Here, we're using the ReLU function, which stands for rectified linear. Basically, this just means that any negative input gets set to 0, while positive input stays the same. You'll see this activation used often with convolutional neural networks, so it's good to be familiar with it. Since we've already multiplied the W1 weights, we just need to add the bias terms here to produce the convolutional layer output. Initialize your variables in TensorFlow, and you have a working convolution. Nice. Let's take a quick look at the fruits of our labor. First, we need to evaluate the H1 node, passing in our example image as the data. So we know where we start. Let's look at the example image here. The 0 here is just because of the strange shaping. There's not really multiple data points. You can see that the values on the diagonal are larger than the other values, just to be distinct from pure random. Let's take a look at the first output feature. Recall that the output H has a shape of 1, 10, 10, 2 because there's 1 data point, 10 pixels in width and height, and 2 features. So to grab the first, we want all the pixels and the 0th filter. Okay, that's interesting. Notice how many positions are zeroed out. That's the rectified part of the ReLU activation. Neat. The second feature should look similar, up to random initialization. These weights haven't been trained on anything yet, so we shouldn't expect them to produce meaningful output. Here we see there happens to be many zeros, but there's otherwise many small values. Your images might look more or less different. The important thing to note is that our output dimensions are the same, but it's like we have 2 different looks at the same image. In this video, we created a first convolutional layer in TensorFlow, mastering the odd shapes required. In the next video, we'll explore a common partner to convolutions, pooling layers. In the previous video, we implemented a convolutional layer in TensorFlow. Now let's understand a common partner to that, pooling layers. In this video, we're going to learn about max pooling layers as being similar to convolutional layers, although they have some differences in common usage. We'll wrap up by showing how these layers can be combined for maximum effect. Suppose you've used a convolutional layer to extract a feature from an image, and suppose, hypothetically, you had a small weight matrix that detected a dog shape in the window of the image. When you convolve this around, your output is likely to report many nearby regions with dog shapes. But this is really just due to the overlap. There probably aren't many dogs all next to each other, though maybe an image of puppies would. You'd really only like to see that feature once, and preferably wherever it is strongest. The max pooling layer attempts to do this. Like a convolutional layer, a pooling layer works on a small sliding windows of an image. Typically, researchers add a pooling layer after one or more convolutional layers. You'll most often see them with window sizes of 2 by 2. All you do is extract the 4 adjacent values. Usually no weights are applied to them. Now, we want to combine these 4 values in a way to extract the most interesting feature of this window. Typically, we want to pull out the most striking feature, so we choose the pixel with the maximum value and throw out the rest. But you could also average the results or do something more exotic. Also, while our convolutional windows had a great deal of overlap, with pooling windows, we usually don't want any overlap, so the stride will equal the window size 2 here. In this 10 by 10 example output, our pooling output is only 5 by 5 because of this change in stride. Another key difference from convolutional layers is that pooling layers often use a different padding scheme, whereas convolutional layers are happy to use same padding and pad out with zeros. We most often use pooling layers with valid padding. This means if a window is beyond the bounds of an image, we throw it out. This does lose some information at the edges, but ensures that outputs aren't being biased by padding values. Note that this example uses a 9 by 9 input to the pooling layer, but because of the valid padding and stride of 2, the output will only be 4 by 4. An 8 by 8 input would also have 4 by 4 output. The real strength of convolutional and pooling layers comes when you combine them. Most often, you'll see a convolutional layer at the top input side of a model, maybe with a 3 by 3 window. This looks for the same set of features anywhere in an image. Then a 2 by 2 max pooling layer immediately follows, pulling out only the regions most exhibiting the features and cutting down the size. You can iterate this process too. After pooling, you now have essentially a smaller image, but instead of pixel color intensities, you have feature intensities. So you can create another convolutional layer to read in the output of the first pooling, and then you can apply another max pooling layer to this. Note how, because of the pooling, the image size is gradually shrinking. Intuitively, you can think of this as building up larger scale features that span larger regions of the image. Early convolutional weights often train to detect simple edges, and successive convolutional layers combine those edges into gradually more complex shapes, like faces, cars, and even dogs. In this video, we explain the workings of max pooling layers, a common convolutional partner. In the next video, we'll put this into practice by adding a pooling layer to our example image. In the previous video, we studied the max pooling layers. Now we'll put them into practice in TensorFlow. In this video, we're going to take a look at the TensorFlow function for max pooling. Then we'll talk about transitioning from a pooling layer back to a fully connected layer. Finally, we'll visually look at the pooling output to verify its reduced size. Let's pick up in our example from where we left off in video 3.2. Make sure you've executed everything up to ### pooling layer before starting this exercise. Recall, we put a 10 by 10 image through a 3 by 3 convolution and a rectified linear activation. Now, let's add a 2 by 2 max pooling layer that comes after our convolutional layer. The key to this is tf.nn.maxpool. The first argument is just the output of our previous convolutional layer, h1. Next, we have this strange k-size. This really just defines the window size of our pooling, in this case 2 by 2. The first 1 refers to how many data points to pull over at once, or the batch. Typically, we leave this as 1. The final 1 refers to the number of channels to include in the pooling at once. Note that here we have 2 channels because the convolution produced 2 output filters, but we only have a 1 in this position. This is to only pull out the max of a single feature at a time. Strides works just like it did in the convolutional layer. The difference here is that we use 2 by 2, the size of our pooling window, because we don't want any overlap. The pre and post 1 values are exactly the same as in the convolutional layer. So our output will be half the size in each dimension, here 5 by 5. Finally, we set the padding to valid. This means that if a window were to go beyond the edge of the image, really the convolutional output, we throw that out and don't use it. If our pooling layer feeds into yet another convolutional layer, you can add that in here. But what if you're done with convolutional layers and want to feed into a classic fully connected layer like in our model from the previous section? This is easy to do. We just need to flatten our output from a 2D matrix with many channels of output to a long one-dimensional vector. This line is one way to automatically compute the length of the flattened pooling output. All it does is multiply the sizes of all the dimensions. So a 5 by 5 matrix with 2 channels would yield 5 times 5 times 2, which is 50 outputs. The next line, tf.reshape, uses this value to actually flatten the array. The -1 here is to handle potential batching of many input images at once. It tells TensorFlow to pick this first dimension such that the overall number of parameters remains the same. Let's peek at the output of our pooling layer so we can see a concrete example. First, we have to actually evaluate our pooling output given our input image. Because the pooling layer depends on the convolutional layer, TensorFlow will automatically put our image through that first. We can look at the results the exact same way as we did for the convolutional output. Just looking at the first filter output, you can notice that it's 5 by 5. Also note that the values present were all in some cell of the convolutional output. Since our only activation on the pooling layer is the maximum, 3 values get dropped in each 2 by 2 window, and 1 advances to the next layer. In this video, we practice creating a max pooling layer in TensorFlow. Now that you're a pro, let's do something more advanced. In the next video, we'll start adding convolutional neural nets to the font classification problem. In the previous video, we implemented a simple pooling layer on a small example. Now let's think big. In this video, we're going to add a convolutional and pooling layer combo to our font classification model. We'll make sure to feed this into a dense layer, and we'll see how this model does. Before jumping into the new convolutional model, make sure to start a fresh IPython session. Execute everything up to numFilters equals 4, and you'll be ready to go. For our convolutional layer, we're going to use a 5 by 5 window with 4 features extracted. This is a little bigger than the example. We really want the model to learn something now. First, we should use tf.reshape to put our 36 by 36 image into a tensor of size 36 by 36 by 1. This is only important to keep the number of channels straight. Now we'll just set up the constants for our number of filters and window as just described. We can set up our weight tensor just like we did in the example problem. Win X and win Y are just window dimensions. 1 is the number of input channels, just gray. And numFilters is how many features we're extracting. Again, it's like the number of neurons in a dense layer. The bias works the same way, but it only worries about the number of filters. The call to conv2d itself is also the same as our example. Good thing we generalized it there to make life easy now. XIM is transformed input. W1 is the weight matrix we just specified. Strides tells TensorFlow to move the window by 1 each step, and the padding equals same means to accept windows over the edge of the image. Now we can put our convolution through the ReLU activation function to complete the convolutional layer. Good job. The pooling layer is also exactly the same as in the previous video. Just to review, we slide a 2 by 2 window, the K size, over the convolutional output, sliding by 2 each time, the stride. When we would reach beyond the edge of the data, the padding equals valid tells us to stop. Now that we have a combined convolutional and pooling layer, let's append a typical densely connected layer. First, we need to reshape the pooling output to be a one-dimensional vector. This is exactly what we did in the last video. We automatically compute the dimensions of the pooling output to get the number of parameters for flattening. Now, let's create a densely connected layer with 32 neurons. Of course, we'll need to initialize our weight matrix with P1 underscore size, the number of inputs to this layer. That's just the flattened array from the convolution and pooling output. And we'll need num hidden, the 32 outputs. The bias term works the same way, with some small non-zero initial value. And here, we happen to be using ReLU activation as well. To finish up, we define the output logistic regression as usual. Working from an old model, just make sure that the final weights use num hidden, 5 for the size. We have a new element here called a dropout. Don't worry about it now. We'll describe exactly what it does in the next video. Just know that it helps with overfitting. You can now initialize all your variables and implement the final call to softmax. Be careful that your variable names match appropriately. Okay, now that setup is complete, let's train it up. We train the model virtually exactly the same way as we did the previous models. Cross entropy measures how wrong our predictions are, and gradient descent adjusts the weights of our matrices. We should also take care to define nodes for our accuracy so we can measure that later. Let's train the model now with about 5,000 iterations. This may take an hour or more, but just imagine if you had to train a different weight for every window in your convolution. With the model trained, let's look at the accuracy curves. Okay, we can see that this model outperforms the old densely connected model, now reaching 76% training accuracy and about 68% validation. Probably this is because a font, even though it creates many different letters, uses many small-scale features in the same way. Let's look at the confusion matrix too. Here, we see that the model is still not perfect, but it's making progress. Class 1 is still underrepresented, but it's at least getting partially correct, unlike in some previous models where it was never correct. The other classes are mostly good. Class 3 here is actually perfect. This isn't an easy problem, so any improvement is good. We also have some code to examine the weights specifically, but we're going to save that for a later video. However, feel free to play around with them here. You can save model weights and information in a checkpoint file. This is pretty simple. You just create a saver object, and then you save the session to a file name. Restoring is just as easy. You tell TensorFlow what session to put your saved files in, and off you go. If you prefer to use NumPy to manually save your weights, the code file also provides functions for that. This can be more convenient because the NumPy format is very portable and reasonably lightweight. If you're exporting values to another Python script that doesn't need TensorFlow, you might prefer NumPy. In this video, we built a convolutional neural network to classify our fonts. Analogous models run on current research problems today. You're at the forefront of deep learning with TensorFlow. In the next video, we'll add even more convolution and pooling to our model. In the previous video, we added a single convolutional and pooling layer combo to our font classification model. Now let's take that a step further. In this video, we are going to add another convolutional layer to our model. Don't worry, we'll walk through the parameters to make sizing line up, and we'll learn what dropout training is. As usual when starting a new model, make a fresh IPython session and execute the code up to numFilters1. Great, now you're all set to start learning. Let's jump into our convolutional model. Why don't we be ambitious and set the first convolutional layer to have 16 filters, far more than the 4 from our old model. But we'll use a smaller window size this time, just 3 by 3. Also note that we changed some variable names like numFilters to numFilters1. This is because we're going to have another convolutional layer in just a moment, and we might want different number of filters on each. The rest of this layer is exactly as it was before. We convolve, then do 2 by 2 max pooling, and we use the rectified linear activation unit. Now we add another convolutional layer. Some models do several convolutions followed by a pooling layer. Others do one convolution, then one pooling, then one convolution, and so on. We're doing the latter here. Suppose you want 4 filters and a 3 by 3 window. This is easy to make weights for. The only big difference from the previous layer is that we now have many input channels. See numFilters1 there? That's because we have 16 input channels coming from the previous layer. If we had used numFilters1 equals 8, we'd have only 8 input channels. Think of these as low-level features that we're going to build on. And remember, the number of channels and the input is like the number of colors. So if you want to think about it like that, that might help you. When we do the actual second convolutional layer, make sure to pass in the output from the first pooling layer, P1. Now, this can go into a new RelU activation function followed by another pooling layer. As usual, we do 2 by 2 max pooling with valid padding. Flattening the pooling output for a convolution follows the same process as the last model too. This time, however, we work on pooling output 2, of course, getting its number of parameters from all its features and the window into one big vector. Now we insert a densely connected layer into our neural network, just like we've done in previous videos. Just make sure to update the variable names. Now we see the same tf.nn.dropout that we used but didn't explain in the last model. Dropout is a way to temporarily cut a neuron out of our model. We do this during training to help avoid overfitting. Each batch, TensorFlow will pick different neuronal output at this connection layer to remove. This helps the model be robust in the face of small changes during training. The keep prob is the probability of keeping a particular neuron output. It's common to set this to 0.5 during training. And again, the final logistic regression layer and the training node code is all the same as before. You can execute that now. Now we can train our full convolutional neural net, the apex of our modeling thus far. This model can take several hours to train, so you might want to start it now before the next video. In this video, we implemented a deep convolutional neural net on a real problem. You're fully proficient with deep learning in TensorFlow. In the next video, we'll evaluate just how good this model is. Welcome back. We're going to wrap up deep convolutional neural networks by evaluating our model's accuracy. Last time, we set up the final font recognition model. Now let's see how it does. In this video, we're going to learn how to handle dropouts during training. Then, we'll see what accuracy the model achieved. Finally, we'll visualize the weights to understand what the model learned. Make sure you pick up in your IPython session after training the previous model. Recall that when we trained our model, we used dropout to remove some outputs. While this helps with overfitting, during testing, we want to make sure to use every neuron. This both increases the accuracy and makes sure that we don't forget to evaluate part of the model. And that's why in these highlighted lines we have keep prob is 1.0 to always keep all the neurons. Let's see how the final model did. Just take a look at the training and testing accuracy as usual. The training accuracy here topped 85%, and the testing accuracy isn't too far behind. Not too bad. How good a model does depends on how noisy the input data is. If we only have a small amount of information, both in the number of examples and number of parameters, or pixels, then we can't expect the model to perform perfectly. In this case, one metric you can apply is how well a human could classify images of a single letter to each of these fonts. Some of the fonts are very distinctive, while others are similar, especially for certain letters. Because this is a novel dataset, there isn't a direct benchmark to compare against, but you can challenge yourself to beat the model presented in this course. If you do so, you might want to reduce the training time. Smaller networks with fewer parameters and simpler computations, of course, will be faster. Alternately, if you start using a GPU, or at least a multi-core CPU, you can get dramatic speedups, often 10x or better depending on the hardware. Part of this is parallelism, and part of it is highly efficient, low-level libraries fine-tuned for neural networks. But the easiest thing to do is start simple and work your way up to more complex models, just like you've been doing with this problem. Back to this model. Let's see the confusion matrix. Here, we can see that the model is generally doing a good job on the various classes. Class 1 still isn't perfect, but it's much better than in the previous models. By building up smaller scale features into larger pieces, we finally found some good indicators for the classes. Your images might not look exactly the same. It's possible to get a little unlucky with the results, depending on random initialization of your weights. Let's look at the weights for the 16 features of the first convolutional layer. Because the window size is 3 by 3, each one is a 3 by 3 matrix. Aha! We can see the weights are definitely pulling out small-scale features. You can see certain things like edges being detected, or rounded corners, different things like that. If we redo the model with a larger window, this might be even more apparent, but it's impressive how many features you can spot in just these small patches. Let's also look at the final layer weights, just to see how the different font classes interpret the final densely connected neurons. Each row represents a class, and each column is one of the final hidden layer neurons. Some classes are influenced strongly by certain neurons, while others have minimal effect. And you can see how a given neuron is very important, positively or negatively, for certain classes, while mostly neutral on the others. Note that because we've flattened our convolutions, we don't expect to see obvious structure here. These columns could be in any order and still produce the same results. In this video, we checked out our real, live, and frankly, pretty nice deep convolutional neural network model. In this section, we built up the idea and practice of using convolutional and pooling layers in order to extract small and large-scale features in structured data like images. For many problems, this is among the most powerful types of neural networks. In the next section, we'll look at models with a time component, recurrent neural networks. Hi, welcome to recurrent neural networks. In the previous section, we studied convolutional networks, but now it's about time to move on to a new type of model and problem, recurrent neural networks. In this section, we're going to explain the workings of recurrent neural networks, RNNs, and implement one in TensorFlow. Our example problem will be a simple season predictor with weather information. We will also take a look at skFlow, a simplified interface to TensorFlow. skFlow will let us quickly re-implement both our old image classification models and the new RNN. In this video, we're going to explore recurrent neural networks. Some background information will start us off, and then we'll look at a motivating weather modeling problem. And of course, we'll implement and train an RNN in TensorFlow. In a typical model, You've got some input features X and some output you want to predict Y. We usually consider our different training samples as independent observations, so the features from data point 1 shouldn't impact the prediction for data point 2. But what if our data points are correlated? The most common example is that each data point, xt, represents features collected at time t. It's natural to suppose that the features at time t and time t plus 1 will both be important to the prediction at time t plus 1. In other words, history matters. Now, when modeling, you could just include twice as many input features, adding the previous time step to the current ones and computing twice as many input weights. But if you're going through all the effort of building a neural network to compute transformed features, it'd be nice if we could use the intermediate features from the previous time step in the current time step network. Recurrent neural networks, or RNNs for short, do exactly this. Consider your input x of t as usual, but add in some state, s of t minus 1, that comes from the previous time step as additional features. Now you can compute weights as usual to predict y of t. And you produce a new internal state, s of t, to be used in the next time step. For the first time step, it's typical to use some default or zero initial state. Classic RNNs are literally this simple, but there are more advanced structures common in the literature today like gated recurrent units and long short-term memory circuits. These are beyond the scope of this course, but work on the same principles and generally apply to the same types of problems. You might be wondering how we're going to compute weights with all this dependence on the previous time step. Computing the gradients does involve recursing back through the time computation, but fear not! TensorFlow handles the tedious stuff and lets us do the modeling. To use RNNs, we need a data modeling problem with a time component. The font classification problem isn't really appropriate, so let's take a look at some weather data. Weather.npz is a collection of weather station data from a city in the United States over several decades. The daily array contains measurements from every day of the year. There are 6 columns to the data, starting with the date. Next is the precipitation, measuring any rainfall in inches that day. After this come 2 columns for snow. The first is measured snow currently on the ground, while the latter is snowfall on that day, again in inches. Finally, we have some temperature information, the daily high and the daily low in degrees Fahrenheit. The weekly array, which we'll use, is a weekly summary of the daily information. We use the middle date to indicate the week, then we sum up all rainfall for the week. For snow, however, we'll average the snow on the ground, since it doesn't make sense to add snow from one cold day to the same snow sitting on the ground the next day. Snowfall, though, will total for the week just like rain. Finally, we'll average the high and low temperatures for the week, respectively. Now that you've got a handle on the dataset, what shall we do with it? One interesting time-based modeling problem would be trying to predict the season of a particular week given its weather information and the history of previous weeks. In the northern hemisphere in the United States, it's warmer during the months of June through August and colder during December through February, with transitions in between. Spring months tend to be rainy, and of course winter often includes snow. While one week can be highly variable, a history of weeks should provide some predictive power. First, let's read in the data from a compressed NumPy array. Weather.npz happens to include the daily data as well, if you wish to explore your own model. NumPy.load reads both arrays into a dictionary, and will set weekly to be our data of interest. NumWeeks is naturally how many data points we have. Here is several decades worth of information. To format the weeks, we use a Python datetime.datetime object, reading the stored string in year, month, day format. We can use the date of each week to assign its season. For this model, because we're looking at weather data, we use the meteorological season rather than the common astronomical season. Thankfully, this is easy to implement with a Python function. Grab the month from the datetime object, and we can directly compute the season. Spring, season 0, is March through May, summer is June through August, autumn is September through November, and finally winter is December through February. And here's the simple function that just evaluates the month and implements that. Let's note that we have 4 seasons and 5 input variables and say 11 values in our history state. There. Now you're ready to compute the labels. We do this directly in one-hot format by making an all zeros array and putting a 1 in the position of the assigned season. Cool! You just summarized decades of time with a few commands. As these input features measure very different things, rainfall, snow, and temperature on very different scales, we should take care to put them all on the same scale. Here, we grab the input features, skipping the date column, of course, and subtract the average to center all features at 0. Then, we scale each feature by dividing by its standard deviation. This accounts for temperatures ranging roughly 0 to 100, while rainfall only changes between about 0 and 10. Nice work on the data prep. It isn't always fun, but it's a key part of machine learning and TensorFlow. Okay, let's jump into the TensorFlow model. We input our data as normal with a placeholder variable, but then you see this strange reshaping of the entire dataset into one big tensor. Don't worry, this is because we technically have one long unbroken sequence of observations. Y bar is just our output. We'll be computing a probability for every week for each season. Cell is the key to the recurrent neural network. This tells TensorFlow how the current time step depends on the previous. In this case, we're going to use a basic RNN cell, so we're only looking back 1 week at a time. Suppose that it has state size, or 11, values. Feel free to experiment with more exotic cells and different state sizes. To put that cell to use, we're going to use tf.nn.dynamicRNN. This intelligently handles the recursion rather than simply unrolling all the time steps into a giant computation graph. As we have thousands of observations in one sequence, this is critical to attain reasonable speed. After the cell, we specify our input x bar, then dtype to use 32 bits to store decimal numbers in a float, and the empty initial state. We'll use the outputs from this to build a simple model. From this point on, the model is almost exactly as you would expect from any neural network. We're going to multiply the output of the RNN cell with some weights and add a bias to get a score for each class for that week. Note that we do need to do this reshaping in order to get things in the proper size again, since we have one long sequence. Our categorical cross-entropy loss function and training optimizer should be very familiar to you. Great work setting up the TensorFlow model. To train this, we'll use a familiar loop. Since this is a fictitious problem, we're not going to worry too much about how accurate the model really is. The goal here is just to see how an RNN works. You can see that it runs just like any TensorFlow model. If you do look at the accuracy, you can see that it's doing pretty well, much better than the 25% random guessing, but still has a lot to learn. Whew! You learned a lot in this video, going from simply understanding RNNs to implementing them in a new TensorFlow model. In the next video, we'll look at a simpler interface to TensorFlow called skFlow. In the previous video, we looked at recurrent neural networks in TensorFlow, but the models are getting complicated to specify, so let's step back and learn about skFlow. This time, we're going to use skFlow to quickly build and train a swath of models. We'll learn that skFlow is an official part of TensorFlow that strives to be like the sklearn or scikit-learn module for Python. Then, we'll build a few simple models with skFlow and finally wrap up with a custom model. skFlow, or scikit-flow, and sometimes called tflearn, though another library goes by that name too, is a simplified interface to TensorFlow. If you're familiar with the classical machine learning Python module sklearn, you'll find that skFlow uses the same style. If you want to learn more about sklearn, you can check out its webpage, scikit-learn.org, for a wealth of documentation and examples. As of TensorFlow 0.8, skFlow comes pre-installed. If you're using an older version of TensorFlow, however, you can install it alongside by following the installation directions on the skFlow GitHub page shown here, github.com/tensorflow/skflow, or by just calling this line here, pip install github.com/tensorflow/skflow/archive/master.zip. First, to use skFlow, you should import tensorflow.contrib.skflow as skFlow. And if you have sklearn, you could import that here too. After loading in your data exactly the same way as in the earlier font classification models, let's do some logistic regression with skflow. In skflow, specifying the model takes one line of code. The key is the skflow.tensorflow linear classifier class. It sets up a straightforward logistic regression if we simply specify the number of classes. Here, we also set the number of steps for training. This is the number of total batches to look at rather than the number of epochs. But steps divided by batch size gives you the number of epochs. By default, the batch size is 32, so we don't even need to alter it. Let's do 1000 steps just to get a feel for how skflow works. For fun, we'll use the atom optimizer instead of gradient descent. And the continue training just keeps our weights around if we make multiple training calls. Like model specification, training is also one quick line. You might notice that there's no loss function. It defaults to something sane like categorical cross-entropy for classification problems. skflow is also nice in that it gives you an output summary at every 100 steps, letting you know that the loss is improving. Let's take a quick look here. Also note that we passed in the train labels directly. We didn't have to convert them to one-hot format, saving us some effort. If you have the actual sklearn installed, easy to do via pip if you don't, you can use it to score the accuracy of your model. Classifier.predict will generate the predicted label based on the class with the highest probability for each image. This is exactly what we did before, just a little more convenient. We didn't run this very long, so this model hasn't yet reached its full potential. Creating a deep neural net with skflow is almost as easy as logistic regression. In fact, the only difference is that you use skflow.tensorflow DNN classifier and add a list of hidden units, the number of nodes at each layer of your network. Here, let's just pick 10 nodes for the first layer and 5 for the second. Everything else is exactly the same as before. We call classifier.fit to train our weights, get some summary information, and we can compute accuracy quickly. sklearn proper also contains a convenience function to create the confusion matrix. You can use this with any labels and predicted classes, but it's particularly nice with skflow's classifier.predict. This network is doing an okay job, but again, we didn't train it very long. You just replicated a whole previous section of this series in a few minutes with skflow. Great! skflow doesn't support convolutional models by default, but it does allow for custom models, so we can do the convolutional portion of our model with mostly plain old TensorFlow code, and then take advantage of skflow for the dense layers and training. To do this, we need to write a function that takes our inputs and ends with an skflow logistic regression model using some intermediate values. Recall that this is exactly what neural nets do behind the scenes. Transform data into a new set of features for some statistical model. Since we flattened our data, let's use tf.reshape to put the images back into squares with one gray channel. Now we'll make this funny call to tf.variablescope. This will let us easily access these weights later on. And if we had multiple layers of convolution, we could use a different scope for each but reuse variable names. Note that we're going to use skflow.ops.conv2d, but it works like a simpler version of TensorFlow. We pass in the input, tell it how many filters to compute on each window, and of course specify the window size. Padding defaults to same, so we don't even need to specify that here. But we do need to include a bias term and clarify that the activation is rectified linear, or ReLU, just like in our traditional convolutional model. This call to tf.nn.maxpool should be familiar. It's copied exactly from our pure TensorFlow convolutional model. skflow uses the same data types as raw TensorFlow behind the scenes, so they can easily work together. We also flatten the output in preparation for the densely connected layer, just like we did before. Now we can use the output of the convolution in a dense neural network. Rather than specify the whole thing in TensorFlow, let's use skflow.ops.dnn to quickly describe a layer with 32 neurons and a dropout of 50%. We could have easily made this deep by adding a number to the list with just the 32. For example, you could say 32, 16 to have a 2-layer dense neural network here. Finally,
we call skflow.models.logisticregression with the computed neuron outputs and compare those to the known labels to train. With this function complete, we can create a generic skflow.tensorflow estimator instance. This is just like what we did above, but now we add model fn equals conv skflow, the function we just wrote, so that it uses the convolutional model. Training and metrics work just like before. You just created a custom instance in skflow, mimicking the model in section 3. Nice work.
For one-line skflow models like TensorFlow DNN classifier, you can access the weights with a single method. But for the custom models, it's a bit trickier. The bottom weights are available directly, but higher level weights like the convolution or dense layer are hidden. Thankfully, yours truly was able to figure out how to access these values and contributed an example to the TensorFlow/skflow codebase on GitHub. Let's look at how this works in our code real quick.
You need to call classifier.getTensorValue and then a string indicating what weights you want to pull out. This is where the scope is useful, because we can supply a string of convlayer/convolution/filters:0 to extract the weights from the convlayer scope, conv2d operator. We can do likewise to get the biases. Getting the dense layer weights is similar, but you specify DNN for the DNN op, layer 0 because it's the first and only layer in the deep network operation, and the final linear matrix to get the weights themselves. It's not intuitive, but it is possible, meaning skflow is applicable for a wide variety of machine learning situations. You might wonder why you don't just use skflow for everything, since it's so easy to build models with. While custom models are possible with skflow, you saw how it calls for mixed skflow and raw TensorFlow code. This can get confusing, and especially as the model grows more complex, difficult to manage. At some point, you, the intrepid machine learning professional, spend more effort fitting your custom model into the skflow paradigm than you would need to just write it in TensorFlow. In this video, we re-implemented a multitude of machine learning models quickly by using skflow. In the next video, we'll apply skflow to our weather modeling problem with a recurrent neural network.
Welcome back. In the previous video, we learned how to use skflow to quickly build models. Let's learn how we can use skflow to build an RNN. First, we'll reshape our data to conform to skflow's expectations. Then, we'll carefully walk through the one-line specification of the model. Finally, we'll train the model a little bit and see what kind of results it gives. After importing the weather data again, let's import skflow and sklearn and get to work. Now we're ready to import skflow and sklearn to make our lives easier. The skflow RNN class is expecting a list of sequences to model. In our case, we only have one really long sequence, so we'll use a dummy listify function to put our data into a one long Python list. Likewise, recall that skflow doesn't need one-hot encoded labels, so let's create the actual integer labels with a call to assign season for each week. The class for RNNs is appropriately named skflow.tensorflowRNN classifier. Here, RNN size is our state size from before, so let's use 11 nodes again. The number of classes is still 4 seasons. If you live somewhere with fewer seasons, your model might be a little easier. We define the type of RNN with cell type, passing in a string. RNN just means a basic RNN like we did before. Other options are LSTM for long short-term memory, a type of recurrence that remembers history for a long time and decides to forget when new input makes that a good idea. Another common choice is GRU for gated recurrent unit, which you can think of as an even more nuanced LSTM. Input op fn is how we make use of our data sequence reshaping. This will get run on our inputs before getting passed to the model. Num layers is deceptive. This is actually how many data points in the past we're willing to add to our state. Each data point gets 11 values. Note that skflow doesn't yet have a dynamic RNN, so we do need a finite number of looks back. Let's say we want to look back 8 weeks, just to try something different. The remaining options are just like previous skflow models. Feel free to change them and experiment. We can train the model just like any other skflow model. Even though we have just one sequence, it does the right thing because of how we've transformed our input data. Training for just a short while shouldn't take very long. Let's examine the accuracy using classifier.predict and sklearn's metrics module. This is on the training data itself, so there's some risk of overfitting, but it looks like the model is doing something. Certainly not perfect at less than 70%, but not too shabby for a one-line model and a few seconds of training. From the confusion matrix, we can tell that this particular model has a hard time distinguishing between spring and autumn. This is somewhat expected, as those seasons have similar temperature profiles. The RNN compensates for some of this by being able to look back 8 weeks, but it's not perfect. In this video, we mastered skflow, building and training an RNN model for our weather data. Great work! This section covered recurrent neural networks in theory and practice. We learned how to use skflow for many types of models, quickly modeling problems old and new. In the next section, we'll review our progress on the research problems and discuss the future of TensorFlow.
In the previous section,
we learned about another interface to TensorFlow and RNN models. This section will wrap up our look at TensorFlow, seeing how far we've come and where you can go from here. First, we're going to review our progress on the font classification problem. Then, we'll briefly look at TensorFlow beyond deep learning and where it will go in the future. In this video, we're going to compare our models in the font classification problem. First, we should remind ourselves what the data looks like. Then, we'll inspect the simple logistic, dense neural network, and convolutional neural network models. You've come a long way in modeling with TensorFlow. Before we move on from deep learning, however, let's look back and see how our models compare on the font classification problem. First, let's look at the data again so we don't lose sight of the problem. In fact, let's look at one image that includes all the letters and digits from every font just to see what shapes we have. That'd be a lot of subplots for Matplotlib to handle, so we're going to make a new array, 5 images tall, 5 fonts times 36 pixels, and 62 images wide, 62 letters or digits times 36 pixels. After allocating a 0 array, we can stuff the training images into it. Font and letter are acting as indices, and we're setting 36 by 36 values at a time in the big array. Note that we have a 9 in the train array here because we're only taking one type of jitter, each letter. Let's take a look with a quick call to pcolor mesh. As you can see, we've got the entire alphabet, upper and lowercase as well as digits 0 through 9. Some of the fonts look like others, while font 0 is kind of in its own world, to human eyes anyway. Each font has interesting stylistic properties that we hope our model picks up on. Let's recap each of the models we built to model these fonts and some of their strengths and weaknesses. At a glance, recall that we slowly built up more complicated models and took into account the structure of the data to improve our accuracy. First, we started with a simple logistic regression model. This has 36 by 36 pixels plus 1 bias times 5 classes total weights, or 6,485 parameters that we need to train. After 1,000 training epochs, this model achieved about 40% validation accuracy. Your results may vary. This is relatively poor, but the model has some advantages. Let's glance back at the code. The simplicity of logistic regression means we can directly see and compute how each pixel affects the class probabilities. This simplicity also makes the model relatively quick to converge in training and, of course, quick to program, as it takes only a few lines of TensorFlow code. Our next model was a single hidden layer densely connected neural network with a final softmax activation layer equivalent to a logistic regression. It has 36 by 36 pixels plus 1 bias times 128 nodes plus 128 hidden nodes plus 1 bias times 5 classes total weights, or 166,661 parameters. The hidden layer uses a sigmoid activation function to achieve nonlinearity. After 5,000 epochs, this tangle of parameters reached about 60% validation accuracy, a considerable improvement. The cost for this improvement, however, was a huge increase in the number of parameters and computational complexity, which you can get a sense of just from the code. And we can no longer have a simple function of individual pixels to class probabilities. But this required only a few more lines of coding, and does perform better. The deep neural network took this one step further, consisting of 128 nodes on the first layer feeding into 32 nodes on a subsequent layer before feeding into softmax for a total of 170,309 parameters, not that many more really. After 25,000 epochs, we achieved a marginal improvement of 63% validation accuracy. A deeper still model might have done better, but this demonstrated some of the strength of deep learning, handling considerable nonlinearity, and this again took marginal extra programming effort. The densely connected neural nets worked reasonably well, but fonts are defined by their style, not specific pixels. Recurring local features should be big clues to a model. We captured some of these local features with convolutional neural networks. We started with one convolutional layer, a 5x5 window computing 4 features with 4 extra bias terms, extracted interesting local parameters using a rectified linear unit. We followed this with a 2x2 max pooling layer applied to each feature, reducing the number of intermediate values to 18 by 18 by 4 plus 1 bias. Flattening these out to 1,297 numbers and putting into 32 nodes of a dense neural net, followed by softmax activations, finished the model with a total of 41,773 parameters. That's a nice cut down on the overall size of the model, although the implementation in code takes more effort than before. After training for just 5,000 epochs, we cleared 68% accuracy. We did have to code up the convolution, but this wasn't so challenging. By applying a little knowledge about the structure of the problem, we simultaneously reduced the model size, yet increased the accuracy. Nice job on that one. Combining the deep and convolutional approach, we finally created a model with several convolutional layers. Though we used a smaller 3x3 window, we computed 16 filters on the first convolutional layer. After a 2x2 max pooling, we did it again, with another 3x3 window and 4 filters on the pooled values. Another pooling layer again fed into 32 densely connected neurons and softmax output. Because we have more convolution and pooling before feeding into a dense neural net, we actually have fewer, 10,765 to be exact, parameters in this model, nearly as few as the logistic regression model. And yet, with 6,000 epochs, the model topped 80% validation accuracy, a testament to your new deep learning and TensorFlow skills. In this video, we reviewed how we climbed from a humble logistic regression model to flying high with a deep convolutional neural net to classify fonts. In the next video, we'll talk about the future of TensorFlow and where you can fit into it. Welcome to the final video, where we'll look into the future. In this video, we're going to observe how TensorFlow is changing, who's starting to use TensorFlow, and how you can make an impact contributing to it. Since its release in late 2015, TensorFlow has already seen several more releases. It's constantly being updated. Although it is an official Google product, it's also open source and hosted on GitHub. As of this video, TensorFlow is at its release 0.8, not even 1.0 yet. The most recent release added distributed computing capabilities. These are beyond the scope of this course, but generally speaking, they allow computation across multiple GPUs on multiple machines for maximum parallelization. Under heavy development, more features are always just around the corner. TensorFlow is becoming more popular every day. Several software companies have released machine learning frameworks recently, but TensorFlow stands out in adoption. Internally, Google is practicing what they preach. Their acclaimed DeepMind team has switched to using TensorFlow. Further, many universities with machine learning or data science programs use TensorFlow both for coursework and research projects. Of course, you've already used TensorFlow in a research project, so you're ahead of the game. Finally, other companies large and small are picking up TensorFlow. Now that you're a TensorFlow practitioner, the only limits are your available problems. Okay, and your computing resources. Here's a couple ideas about what you could tackle next with TensorFlow. Plant leaves, like fonts, have similar styles within a species. Can you adapt the models you built in this course to identify a species using just an image? Next, suppose you've got a lot of dashcam footage from a long road trip. Road signs on the highway can give you a lot of information like where you are and how fast you should be going. Can you build a series of TensorFlow models to find, say, the speed limit in footage? Also, commuting takes too long no matter how close you live to work. Given current conditions like traffic and weather, you should be able to build a regression-based model to predict your travel time. Finally, one startup is exploring using TensorFlow for a matching algorithm. Don't be surprised if in the future an algorithm gets you a date. There's too many neat TensorFlow-based projects to list them all, but chances are you'll find something related to your interests, and if not, that's the perfect place to contribute. There are many machine learning libraries, but TensorFlow is here to stay. Though this series focused on deep learning, TensorFlow is a general graph computation library. Deep neural nets are really a sliver of data modeling that TensorFlow happens to handle very well. But as you saw in the video on simple computations, any operation you can specify as a graph, you can do in TensorFlow. One practical example was an implementation of k-means clustering in TensorFlow. More generally, operations that vectorize well and require some kind of training may benefit from TensorFlow usage. All this is to say that you are the future of TensorFlow. TensorFlow is open source and changing all the time, so you can contribute new features easily on GitHub. These can be highly complex new model types or simple documentation updates. All changes can improve the library. The rising popularity of TensorFlow means that you are one of the earliest professionals to master it. You've got an edge in your machine learning career or research. And because it's more than deep learning, whatever field you're in, TensorFlow is probably applicable to some aspect of it. In this section, we fondly recalled our TensorFlow models for font classification, reviewing their accuracy. We also took some time to discuss where TensorFlow is headed. Congratulations! You're now well versed in TensorFlow. You've applied it to multiple research problems and models in this series and learned how it's widely applicable. The next step is to deploy TensorFlow in one of your own projects. Thank you and happy modeling.